hello dear students, welcome back to this rapid revision video. In this class we'll be talking about biostats. This has been divided into two parts, okay? So biostats is very important. One or two questions do turn up. So let us try to give a conceptual as well as crisp review of biostats. Okay? So now what is biostats? Obviously nobody is asking you that, but still what is it? It's the application of statistics in the field of medicine. Okay, that's what is the definition of biostatistics. Okay, now in biostatistics what happens is that we collect a lot of data. Okay, data is nothing but raw numbers. Okay, it's raw values. Values of what? Values of variables. So in biostatistics we are dealing with a term which is very important, variables. What is variables? Anything which can take up a value. Like you have to do a study on college students. Okay, so you're going to definitely ask about their gender. So gender is something which can take up a value, right? How many boys are there in the college? How many girls are there in the college? So suppose, let's say there are 100 boys, okay, and let's say there are 50 girls. So this 150, okay, 100 value and 50 value, this is the data. But these values have been given to this variable. Okay, so variable is anything which can take up a value. And in entire biostat, the first thing which is done is classification of variables. Okay, so let's first start with the types of variables or classification of variables. Okay, so in this, variables can be divided into two types. Okay, one is quantitative. This is the major classification, quantitative, and the other is qualitative. Okay, quantitative variables are variables which can be measured. Okay, they can be what? They can be measured as well as they can be compared. But what is qualitative variables, guys? Qualitative variables cannot be measured, okay, cannot be measured, and they cannot be compared. Okay, they cannot be compared. What do I mean by this? What do I mean when I say can be measured? Measured matlab it has some unit. Okay, it can be measured in some unit. Example, weight. Weight can be measured in kilogram, grams. Height can be measured in centimeters, feet. Okay, hemoglobin, it can be measured in gram per dl. Plus we can compare also. My hemoglobin can be less than yours, or your hemoglobin can be more than your friends. Your weight could be more than somebody else's or less than somebody else's. So the important thing that you have to remember is quantitative are which can be measured. That means they have a unit, plus they can be compared. And what is qualitative? They cannot be measured, cannot be compared. What do I mean by this? Like religion. Okay, blood group. Okay, gender. Now, if I say I'm A positive, you are B positive, or even if you are A positive, can we measure blood group in a unit? Do we have any unit for blood group? No, we don't have any unit for blood group. Plus, if I am A positive, you are also A positive, can I say I am more A positive than you? No, we can't do that. Okay, gender. Now, male, female, transgender. Can we measure gender in any unit? No. All right, religion. Anybody can be a Hindu, Muslim, Christian and all that. Can we measure religion? No, we cannot measure religion. Okay, anemia. Now see, anemia. You could be iron deficiency anemic, megaloblastic anemic. But can I measure anemia? No, I can measure hemoglobin. So hemoglobin is definitely quantitative. Okay, so whenever you get any variable, you just see whether you can measure it and whether you can compare it or not. Measure means is there a unit or not. Okay, the other classification of variable, everybody, which will come in your exam is continuous and discrete. Now what is continuous? Continuous variables are variables which can take up many possible values. Okay, so let us write over here, take up many possible values and also in between values. But what are discrete variables? They can take up fewer values and no in between values. What do I mean by this? When I say continuous variables are variables which can take up many possible values and also in between values, means they can be expressed in decimals. Okay, they can be expressed in decimals. The values can take up even decimal points. Okay, but here no decimals. Okay, they are discrete. Okay, they take up fewer values. So remember one thing, all the quantitative variables, guys, all quantitative, all right, all quantitative variables are continuous, and all qualitative variables, okay, all qualitative variables are discrete. Okay, example, now if you see height or if you see weight, weight could be 20 kg, 20.1, 20.2, 20.3, 21 kg. So it can be expressed in decimals also. Okay, it's something which can take up many possible values and also in between values. Okay, hemoglobin. But when I say qualitative variable, when I say discrete, now gender could be male, female, transgender. Nobody can lie in between. Okay, blood group, you can be A positive, B positive, AB positive. You cannot lie in between A positive and B positive. So you're taking up fewer values. Okay, anemia. Now you can be iron deficiency, megaloblastic anemia. You can't lie in between. All right. So discrete may mostly we have all the qualitative variables are discrete and all the quantitative variables are continuous. Okay. Now suppose I say age in years and months. Okay, age in years and months. What is this? And if I say age group, all right, if I say age group like 15 to 20 years and 21 to 25 years. Now what is this? See, if I say age in years and months, if I say that means 20.2 years, somebody is 20 years, 2 months old. Okay, so this becomes which type of variable? Continuous. Why? Because this can be expressed in decimals also. Okay, but if I say 15 to 20 years or 21 to 25, either you're going to fall in this group or you're going to fall in this group. You can't lie in between. You will go to either of the groups. So when you see age group, it becomes discrete. Okay. All right. What is one more classification of variable, everybody? So one more classification is dichotomous and polyotomous. Now what is dichotomous? Dichotomous are variables which can take up two values. And what is polyotomous? They can take up more than two values. Okay, now here either the qualitative, quantitative, they can both be dichotomous, polyotomous. Like if I say weight is polyotomous, it can take up so many values. Okay, if I say presence, absence of a disease. Okay, now if I say presence, absence of a disease, so when I say presence, absence of disease, either you're going to have a disease like let's say hypertension or not have. So it becomes what? Dichotomous. This is taking up only two values. And will it be continuous or discrete? Discrete. So I'll just put it here for your reference also. Presence, absence of disease, right? Presence, absence of disease. This can take up just two values, right? It has only two values. Either you'll have the disease or you won't have the disease. All right. If I say religion could be Hindu, Muslim, Christian, Sikh, so many things. Okay. So quantitative, qualitative, both can fall in either of the groups. Okay, now here let me ask you one question. Suppose I ask you pulse rate. What do you mean by pulse rate? Can you express it in terms of all the three classification? Now if you count your pulse, you can say it is 80 beats per minute, 78 beats per minute, whatever. Okay, but if I ask you count your pulse rate for 2 minutes and you count it as let's say 163 in 2 minutes. Okay, 163 in 2 minutes. So in 1 minute, how much is it going to be? 81.5. So can you see we can express pulse rate in decimals, right? So pulse rate is actually which type of variable? It is actually quantitative and it can be expressed in decimals. So it is continuous plus it is polyotomous. It can take up so many possible values. Okay. Plus, can you measure pulse rate? Of course. We can measure pulse rate in beats per minute. There is a unit to measure pulse rate, right? So whenever you get a classical, it's just the limitation of human brain that we miss the decimal points while counting. Okay, so remember this classification of variables. So look at this, blood pressure is which type of variable? Now here we're going to come back to this question because here you can see one more term, nominal. Leave that, otherwise tell me qualitative or discrete or continuous. So qualitative variables are discrete, blood pressure is continuous. Why? Because you express it in an unit. millimeter Hg plus my blood pressure and your blood pressure we can compare also. Okay, nominal I'll just be telling you. Which of the following is a continuous variable? Now blood group. Like I said, A positive, AB positive, B positive. Is it continuous? No. These are taking up fewer values. You cannot lie in between. It cannot be expressed in decimals. Religion, sex, same thing. Weight, of course, is continuous. It can be measured in kg. It can take up many possible values and also expressed in decimals. Okay? Now, all these variables can be expressed in a scale of measurement, in different scale of measurement. Okay? Broadly, the scale of measurement is categorized into categorical scale, everybody, and dimensional/metric scale. Now remember one thing, dimensional/metric, as the name only sounds, this is used to express all the quantitative variables. Okay, so all the quantitative variables can be expressed via dimensional or metric scale, but all the qualitative variables, okay, all the qualitative variables, everybody, will be expressed via a categorical scale. In the categorical scale, we further divide it into two. One is a nominal scale and one is a ordinal scale. Now, as the name suggests, nominal scale is based on names, okay, and as the name suggests, ordinal, it is based on order. Now, what do I mean by this? In an ordinal scale, I can express the variable in an order. Okay, like example, staging of cancer. Okay, staging of cancer, we can have stage 1, stage 2, stage 3. That's an order. Stage 1 is better than stage 3, right? Likert scale. Likert scale kya tha? You can see in the main videos also. Rate your performance in the exam. Okay, you were dissatisfied, satisfied, unsatisfied, or something like that. Okay, where you can rate your performances on a scale of 1 to 5. Okay, then you have other things like Glasgow Coma scale, Child Park score. All of this you can do a scoring. Okay, you can put it in an order. If I say grade hypertension, okay, grade hypertension, mild, moderate, severe, so that is again an ordinal scale. Okay, we can grade hypertension into mild, moderate, or severe. Okay, then severity of anemia. Okay, severity of anemia, mild, moderate, severe anemia. So you can put it in an order. But in nominal scale, what happens if I ask you type of anemia? Okay, type of anemia, now I can put it in an order. Either you are iron deficiency, megaloblastic, sideroblastic, whatever. That's what? That is the type of anemia. I can't say that is good or that is bad. Okay, then type of delivery. Okay, now if I say type of delivery, somebody can have a normal delivery, somebody vaginal, somebody C-section, right? So can you put it in an order? Can you see normal is good, C-section is bad? ऐसा नहीं बोल सकते. We can't say that. So type of delivery again is a nominal scale. Okay, if I say gender, male, female, transgender, we can't put it in a scale. That becomes nominal. So wherever you can put in an order, this is most commonly asked, guys, ordinal scale. They will give you a lot of examples and they'll ask you which scale of measurement. Okay, so that is ordinal and the other one is nominal. But they are both belonging to categorical scale, which measures qualitative variables. For quantitative, we have two types of scales which are known as interval and ratio scales. Okay, so these are used to measure quantitative variables. Okay, now just see over here. Categorical mein there are nominal and ordinal. Nominal is based on names, ordinal is based on an order, and these are used to represent qualitative variables. Okay, then you have dimensional or metric scale like interval scale and ratio scales. Now, what are these interval and ratio scales? Just read it with me once. Interval scales hota hai metric data without an absolute zero and no start point. But ratio scales are metric data with an absolute zero. Okay, so this is just an example of interval and ratio scales like temperature in Fahrenheit. That is interval scale. But if I have to express LDL, HDL, all that can be expressed in ratio scales. Okay? Most commonly, but they ask you about the categorical scale, nominal and ordinal. See over here, satisfied, very satisfied, dissatisfied. So is it at an order? Yes. So this becomes an ordinal scale. An investigator studies into the life expectancy of IV drug abusers, divides a sample of patients into HIV positive and HIV negative group. So either somebody is going to be a HIV positive or HIV negative. Is it an order? No, that's not an order. It's simply based on Names, nominal scale. Either you have or you don't have a disease. So presence or absence of a disease, everybody, okay? Presence or absence of a disease is which type of scale? Nominal scale. But if I say, like, do you have anemia? Your answer is yes or no. That is nominal. But if I ask you, grade your anemia, is it mild, moderate, severe? That is ordinal scale. So all qualitative variables will belong to nominal or ordinal scale. All quantitative variables will go into metric or dimensional scale. Okay? That was the first part. Quick revision done. Now let us see what is measures of central tendency. See, this is a very commonly asked topic, a very repeated topic. Okay, now what do you mean by central value? Please remember, central value is that value. Okay? Which is it is that value which is most representative of any data set. Okay, like suppose in a class there are 50 students. Okay, so everybody has a weight. Okay, somebody has like 50 kg, 62 kg, 61 kg, 58 kg, 50 kg again. So everybody has a weight, but there's going to be one value, okay, which is going to be the most representative of all these weights. Okay, that value will be in the center and all the individual weights will revolve around it. Okay, so whenever you say measures of central tendency, it's the most representative value. Now, depending on the type of variable, this central value can be mean, median or mode. So, depending on the type of variable that we are talking about, okay, depending on type of variable, okay, this central value, what could it be? This central value can be mean, it can be median, or it can be mode. Never say central value is only mean. No, it can be mean, median, or mode. So let us start with the first one. What is mean, everybody? Mean is sum of all observations divided by the total number of observations. What do I mean by this? Example, if I give you a data 2, 1, 3, 2, 5, ask you calculate the mean. So what will you do? You will add up all the observations, 2 plus 1, 2 plus 1 plus 3 plus 2 plus 5. 1, 2, 3, 4, 5. How many total number of observations? 5. So 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 by 5, right? Okay, so 5 2s are 10. So what is the mean over here? 2.6, right? Okay, so this is what sum of all observations divided by total number of observations. Remember one thing, mean is statistically the best measure of central tendency. Okay, it's statistically the what? It's statistically the best measure of central tendency. Why is it statistically the best measure of central tendency? Because it includes all values, okay, or it takes all values into consideration. So it is statistically the best measure of central tendency is mean. Okay, next one, what is median? Please remember, median is the middle value. Okay, middle value. When what happens? When data is arranged in ascending / descending order. Okay, it is the middle value when data is arranged in an ascending order or a descending order. Don't forget to arrange it in an ascending or descending order. Mostly we arrange it in an ascending order. Like suppose I give you 2, 1, 4, 1, 5. Now what is the median over here? You can see that the middle value coming over here is 4, but is it actually the median? You have to first arrange it in an ascending order. So when I arrange in an ascending order, it will be 1, 1, 2, 4, 5. Now over here 2 values are above, 2 values are below, so median is 2. Now over here it was very simple because total number of observations was 5, okay, which is odd. So when we have odd number of observations, median is equal to the middle value when data is arranged in ascending or descending order. But when we have even number of observations, okay, when n is equal to even number of observations, guys. What is median? What is median in that case? In that case, median is equal to the average of two middle values. Remember this, okay? Average of two middle values. Meaning, suppose if I have 2, 1, 4, 1, 2, and I also have 3. So now over here 1, 2, 3, 4, 5, 6. Total number of observation is 6. So first I'm going to arrange in an ascending order 1, 1, 2, 2, 3 and 4. Okay, so this is now what is going to be your median? It is going to be the average of the two middle values. That means these two values are above, below. So when I have to calculate the median, it is average of the two middle values. So that is 2 plus 2 divided by 2. So that is 2. Got it? Did you understand? Whenever median you have to calculate, it is the middle value. But please don't forget to arrange your data in ascending or descending order. In odd number of observations, it's simply the middle value. But when you have even number of observation, it becomes what? It's the average of the two middle values. Okay, so that is the thing about median. Now remember one thing, median is the best measure of central tendency. As discussed in the main videos also, it's the best measure of central tendency in case of skewed data. Now what was skewed data? If you remember, skewed data is a data set, okay, where outliers are present, okay, outliers are present. And what were outliers? Too high or too low values. Okay, if we have extremely high values or extremely low values, they tend to tilt our data set, okay, either towards the right or towards the left. So when we have too high or too low values, that is known as outliers. Okay, in that case, median becomes the best measure of central tendency. Okay, like I'll just quickly give you an example. Suppose here I have a data set 20, 10, 30, 40 and 50. Okay, now if you have to calculate which central tendency measure will be best for this. Now, does this have any value which is outside, which is too high or too low? No. So, the best measure would be mean. Why? Because no outliers here. But if I have a data set which is like say 300, 400, 100, and then instead of 500 by mistake I copied 5000. Okay, and then again 100, 200. Now this 5000 feels out of place over here. Okay, so this is an outlier. Now for such a data set, median will become the best measure of central tendency, because when you're going to arrange it in an ascending or descending order, this too high value is going to go towards one extreme, right? So it will not affect our main answer. Okay, so just remember, technically, statistically, best measure of central tendency mean. But when we have outliers which tend to skew my data set, the answer becomes median. Okay, mode is what? Very commonly asked, most repeated value or most frequently occurring value in a data set. Okay, most repeated value or most frequently occurring value. Okay, most frequently occurring value in any data set. Okay, so if you have, let's say 2, 1, 1, okay, 2, 4, 3. What is the mode? So what is most frequently occurring? 1 also and 2 also. So this is 1 and 2. So this is what? Bimodal. Sometimes you can see that they have converted bimodal into unimodal. So how do you convert bimodal into unimodal? So to convert bimodal into unimodal, you again have to take the average. So 1 plus 2 by 2. Okay, so 3 by 2, 1.5. But always try to give your answer as bimodal. Okay, so that is the most repeated value in a data set. See, now over here, best central tendency, the values 18, 20, 22, 24, 26, 28, 30. Now, if you see this data set, it is within normal range. It is within a normal range. Okay, there is, what do I mean by this? That there are no outliers here. So when there are no outliers, my best measure is mean, because it is going to consider all observations. Okay, when I calculate mean, it is going to take all observations. Range, don't worry, it is a measure of dispersion which we are just going to revise. But now look at this data set. The number of malaria cases reported during the last 10 years in a town: 250, 320, 190, 300, 5000, 100, 260, 350, 320, 160. Now here this 5000 becomes an outlier, which is going to tilt my data to the right or the left, because this is at extremely. Why is it an outlier? It is too high value, right? What is it? It is too high value. Okay, but when I take the mean, if I calculate the mean, I will have to add up 5,000. So mean will give me an exaggerated answer. All right, but when I calculate median, okay, that is the best. Why? Because when I arrange this in an ascending order, 5,000 is going to go towards one end. So it's not going to affect my final this thing. So the answer becomes median. Don't worry about arithmetic mean, geometric mean. We are calculating arithmetic mean. Geometric mean includes algorithms. So that's logarithms. So that's not done over here. So what you need to remember for statistically, if somebody asks you, the best measure of central tendency is mean, but if it's a skewed data set with outliers, the best measure of central tendency becomes median. Okay? Bimodal distribution, this is just a formula. If you're given median and mean value, mode is 3 median minus 2 mean. Alright, now before we go to the next topic, remember you had a nominal scale of measurement. Nominal, ordinal and metric scale. So if somebody asks you, which measure of central tendency, okay, which measure of central tendency best represents these scales? Okay, so for nominal scale, which measure of central tendency would you prefer, mean, median or mode? For ordinal, now see, ordinal was an order, right? You arrange in an order. Okay, so in median also you are arranging in an order. So for ordinal it is median. Okay, metric is dimensional or metric scale, so it is again dealing with mean. But nominal may mode. Now you know nominal was based on names. Okay, most, how many, like if I say it's based on the most frequently occurring value. Are there more number of boys in the class or are there more number of girls? So which value is repeated most often? And what is the definition of mode? The value which is repeated most often. Okay, so this is the golden point. Okay, so that was about central tendency. You need to revise the formula of mean, median, mode, very important. And you also need to know the concept of what is the best measure of central tendency for skewed data set and what is the best measure otherwise. Okay, all right, next is measure of dispersion. Now see, dispersion is used to denote how the data is spread. So it denotes what? Spread of values in a data set. Okay, spread of values in a data set, or it represents variability in a data set. Now, like I said, suppose there are 50 students. Everybody has a weight. Now, when we calculate the mean, it comes out to be 50 kg. That doesn't mean that all the students have a weight of 50 kg. Okay, somebody could have 52, 54, 56, 48. So, all those individual weights, okay, are scattered around this mean weight. Now, are they closer to the mean weight or are they farther away from the mean weight as given by measures of dispersion? So, whenever, and this measure of dispersion can be assessed for individual observations also, like we have studied, okay, and also for sample observations. Okay, sample observations means what? Suppose I have a class of 10,000 students. Can I take everybody's weight? No. So I just take out a sample. I take a sample of only 100 students and take their weight. So that sample will also have a mean weight. Okay, so when I take sample observations, how sample means, okay, how sample means are distributed around population means. Okay, so when I say sample means are distributed around population means, what was the best measure of dispersion? Standard error. Okay, remember that. But when I say how individual values are dispersed around central value, the best measure over here was standard deviation. Okay, you just have to know the formula how individual values are dispersed around the central value. For that we have standard deviation, but whenever we are considering sample observations, in that case we have standard errors. Okay, so what are the measures of dispersion that we are going to study? We'll just be looking at the formulas, guys. Okay, number one, you should know what is range. Number two, the most important one that you need to know, everybody, there is something known as mean deviation. okay, and there is something known as standard deviation. The most frequently and the most commonly used is measure of dispersion is standard deviation. Then you need to know just two formulas over here, coefficient of variation, okay, coefficient of variation, we'll be revising this formula, and there is one more, variance, okay, we need to know this formula. Other than this, if I talk about sample observations, then you have to remember the formula of standard error of mean, okay, and the formula of standard error of proportion. These are like must know formulas, okay. This is like most of this chapter of measures of dispersion deals with a lot of formulas, okay. So let us quickly revise the formula for range. So if you remember, range was the difference between maximum value minus the minimum value. That means, suppose if there is a class of 100 students, okay, there was a class of 100 students, and in this the maximum weight everybody of a student was 100 kg, okay, and what was the minimum weight over here? The minimum weight of a student was 50 kg. So they will ask you directly to calculate the range. So that will be maximum minus minimum, 100 minus 50, 50 kg. That means what? No two students weight in the class differs by more than 50 kgs. Okay, this could also be asked. Interpretation means no two students, okay, weight in the class, no two students weight in the class differs by what? Differs by more than 50 kg. कोई भी ऐसे दो बच्चे नहीं हैं जिनके weight में difference 50 kg से ज़्यादा है. Okay, so that is what is range. Okay, this calculation definitely comes. Then another one is mean deviation. To understand mean deviation, let's study standard deviation also together. Okay, so now suppose if there were 50 students in the class. Okay, so everybody mu I matlab individual weight. Everyone has an individual weight. Okay, let's see, this one has 50, 52, 51, 60, something like that, 54. Okay, so I have 50 weights with me. I calculate mu. Mu means the mean weight. Now, when I calculate the mean weight, let's say it comes out 50, 50, 50. So, what was my next step? If you remember, mu I minus mu. So, जैसे यहाँ 0. Okay, 52 minus 50 will be plus 2. 52 minus 50 will be plus 2. Okay, but suppose I have 48 somewhere. 48 minus 50 will be minus 2. So when you sum up this, okay, you will see all positives are going to cancel out all the negatives. So this will become equal to 0. Therefore, in the next steps, what do we do? Mu I minus mu whole square to remove this effect of positives and negatives. And then we, like, this will also be 4, this will also be 4, just to make you understand. Then we sum it up. Okay, mu I minus mu whole square का sum कर दो. Now, in the final formula of standard deviation, what is it going to be? Since you squared it, in the final formula, we have to remove the effect of the square. So, we put a logarithm. So, that is mu I minus mu whole square divided by n. Okay. So, this is the formula for standard deviation. But if the sample size everybody is less than 30, then what is the formula for standard deviation? This is sigma mu I minus mu whole square divided by n minus 1. They give you to identify the correct formula when the sample size is more than 30 as well as less than 30. You understood why we put the log? Because we had squared it. Okay. Now, you would ask me, ma'am, what is mean deviation? So, mean deviation is nothing. It is simply, all right, mean deviation is simply like here we are having whole square. Okay, so that is summation of just mu I minus mu divided by n. Okay, no squaring. All right, before squaring, okay, before squaring this process, mu I minus mu divided by n, that is mean deviation. But they don't ask you that. They ask you what is standard deviation. So I'll just give you a question. Okay, interpretation is important. Suppose there are 100 students in a class. Okay, and mean weight, okay, mean weight of the 100 students has come out to be 50 kg. Standard deviation is 5 kg. What do you mean by this? Can you tell me what is the interpretation? This question can come. What is the interpretation of this? This simply means that the weight of students in the class, okay, the weight of students in the class lies between what? The weight of students in the class lies between weight of all these 100 students in the class lies between 50 plus minus 5. That means 45 to 55 kg. Okay, did you understand this? That is what is the interpretation of standard deviation. All right, and suppose there was another class, okay? Suppose there was another class, okay? In another class, there was also 100 students, let's say, okay? And over here, the mean weight mu was 50 kg, but standard deviation, let's say, was 10 kg. So here, what would be the interpretation? It means the weight of students are lying between 50 plus minus 10 kg. That means 40 to 60 kg. Now, which data set is better? This first class one or this second class one? Obviously, this first class, because the dispersion is less, the spread of data is less. But here it is more, 40 to 60, which is more wider distribution. So the data set where you have more wider distribution, that becomes less reliable. Okay. Okay. So what did I just tell you? All right, where we have more spread of data, they become less reliable. All right, so it simply means that the values of dispersion should be less. Okay, more the spread of data, okay, more the spread of data. When I say more the spread of data, it implies more variability. Okay, more variability. This implies what? The data set is less reliable. Okay, less reliability, or you could also say less precise. This is very important. And what was the other way to compare? So one is standard deviation, you can compare. Okay, so if any data set has, one data set has standard deviation as 2 and the other one has 5, which one is more reliable? The one which has lesser standard deviation. Okay, then another thing which comes is coefficient of variance calculation. So this is used to basically compare two data sets. If you will look in the mean videos, you will also see, and the formula for this is coefficient of variation, standard deviation upon mean into 100. Okay, like suppose this is a class of 100 students, mean weight is 50 kg and standard deviation is 10 kg. This is a class of 100 students, okay, mean weight is, let's say, 60 kg, standard deviation is, let's say, 5 kg. So which data set is more reliable? You can calculate COV over here. So that is 10 upon 50 into 100, okay. So since multiplier is 100, it will come in percentage, obviously, and here it will be 5 upon 60 into 100, right? Okay. So, 100 divided by 12 something you will do it. Okay? So, this will come out to be 8.3%. Now, you can see over here that which data set is more reliable. This has a lesser coefficient of variation, only 8.3%. This has more, 20%. That means data set A is more spread. Even if you can see over here, standard deviation is 10. Here it is 5 kg. So, where is the standard deviation less in the sample set B than in A? Right? So which data set is more reliable? B is more reliable. Okay. So what I'm trying to tell you is that if the measures of dispersion are more, the data set becomes less reliable or less precise. And what is the formula for variance, everybody? So the formula for variance is standard deviation squared. Okay. Like in data set A, what was the standard deviation? 10 kg. So sigma 1 is 10. And in data set B, what was the measure of standard deviation? Here it was 5 kg. So if somebody asks you calculate variance, this will just become 100, this will just become 25. So again, which is more reliable? This data set B. So remember this, okay? More the measures of dispersion, okay? This is very important. It's basically a chapter of formulas, okay? More the measures of dispersion, everybody, it implies more variability. More variability means more spread, okay, more spread. So when it is more spread, it becomes what? Less precise. And how can you increase the precision? You can increase the precision, all right, by increasing the sample size. How can you increase precision or reliability? Increase sample size. Very important. Okay, this comes as your MCQ. Okay. Next thing that you need to know is just two formulas. So when you have sample observations, okay, for sample observations, not talking about individual, when I've calculated the mean of a sample, how the mean of a sample is dispersed around population mean. For that, what do we use, guys? We use the concept of standard error. Okay, so what is standard error? Standard error is nothing but deviation of sample means. Okay, it is standard deviation of sample means. Okay, deviation of sample means from which means? From population means. Okay, this is deviation of sample means from population means. Again, this is important. Like, how are the sample means distributed around population means? In this, you just have to remember two formulas. You will get to calculate standard error of mean, which is standard deviation upon square root of n, and standard error of, you can get proportion, okay, which is square root of pq by n. P was what? You can check it out in the main videos also. Prevalence that will be given to us, and Q is always 100 minus P. Okay, I'll just give you a quick calculation. Okay, suppose their sample is of 100 students. Okay, standard deviation obtained is 10 kg. And if they ask you, okay, we are calculating, I'm just trying to show you the calculation. They give you calculate mean weight is, let's say, 50 kg. Calculate, if they write standard error of mean over here, you will use the formula standard deviation upon square root of n. So that is 10 upon square root of 100. So that will be 10 upon 10, so 1. Okay, but if I give you, there is a class of 100 students, okay, mean weight is, let's say, 50 kg, but I don't give you standard deviation. I say that the prevalence of obesity in this class, okay, prevalence of obesity is equal to 10% over here. So now, since I've given you prevalence, I'll ask you to calculate standard error of proportion, guys, not mean. So that is square root of pq by n. Now p is given to us 10. Q कितना हो जाएगा? 100 minus P. Always, if P was 20, 100 minus 20. If P was 30, 100 minus 30. So 100 minus 10, here it will be how much? If I say 100 minus 10, okay, 100 minus 10, so that will become 90. So square root of P is 10 into 90 by 100. So N is 100, so square root of 900 by 100 means square root of 9, which will be 3. Got it? So be very careful. Do you have to use standard error of mean or standard error of proportion? Okay. See, basically in measures of dispersion, don't forget to revise the formula. What is the formula for range? What is the formula for standard deviation? What is the formula for standard deviation when you have sample size less than 30? What is standard error of mean and what is standard error of proportion formula? Now look at this. There are 50 individuals in population and they all have the same hemoglobin level. That is 14. As there is no variability. No variability means no spread. So obviously that means mean is also 14 and everybody is also having value of 14. No spread, so standard deviation 0. Any which way, see, this was like there are 50 students, okay, and they have same hemoglobin level. So everybody has 14, 14, 14, 14. This is mu I. If you calculate mu also over here, mean hemoglobin, you have to sum up this. Okay, if you sum up this 15 to 14, okay, everybody has 14 divided by 50 individuals, you will get 14 only. So when you do mu I minus mu, this is going to come 0, 0, 0. If you square it also, everybody, this is going to remain 0, 0, 0. So no variability. So the answer is 0. Okay. Now, when these individual values or sample values are spread around central values, okay, they take up a certain pattern of distribution. So, when we study distribution, it will be of two types, normal or skewed. Okay. So, let's first quickly revise the points of all the normal distribution. See, this is how a normal distribution curve looks like. Okay, so the first thing you need to know is a normal distribution. Normal distribution का simple मतलब क्या होता है? What is the meaning of this? This means that this has no outliers. Okay, no too high or low values. All the values are within a defined range. There are no very extremely high or low values. Okay, so there are no outliers. This is also known as what? This is also known as Gaussian distribution because it was discovered by Gaussian. Now, what is the first point? You can see this is what? This is a bell-shaped curve. Okay, what is the second point? The second point is if I drop a line over here, okay, in the middle, okay, it's going to, it gives it the shape of bilaterally symmetrical, okay, bilaterally symmetrical. What does this mean? That both the sides are exactly mirror images of each other, okay. This has cut it into 50% above and exactly 50% below. Okay, all right, so that is very, very important. What is the third point? This point is known as POC. What is POC? This is point of coincidence. Now, what is happening in this point of coincidence? Everybody remember, mean is equal to median is equal to mode. Okay, at this point of coincidence, what is the coincidence? That mean, median, mode are all equal. It could be 100, 200, 20, 30, anything. But when at the point of coincidence, mean, median, mode is equal to 0, then it will be known as standard normal curve. Okay, so anybody can ask you, what is the difference between normal curve and standard normal curve or standard normal distribution? Over here, at the point of coincidence, mean is equal to median is equal to mode is equal to 0, everybody. That's the coincidence. That mean, median, mode all have become equal to 0. Okay? That's very important. And what is the spread? How much is the spread of data? Now you can see 50% above, 50% below. So it's almost equal distribution. You can also write it as 0.5 and 0.5. So next point, if somebody asks you the total dispersion over here, okay, so the total dispersion over here becomes how much? It is 0.5 plus 0.5. So it is equal to 1. And what is this dispersion? Nothing but SD. So for a normal distribution curve, please remember, correct representation. So many times they ask you, correct representation is equal to, mean is equal to 0 and standard deviation is equal to 1. Okay? Plus, if somebody asks you, what is total area under curve? So what is the total area under curve? Nothing but 0.5 plus 0.5. So that is equal to 1. Okay, so look at this, bell shaped, bilaterally symmetrical. At point of coincidence, mean, median, mode all are equal, which could be equal to anything. But if they are all equal to 0, it is known as standard normal curve. So total dispersion is 1. So correct representation, which is very important, mean is 0, standard deviation is 1. And total area under the curve becomes equal to 1. Okay, one more thing over here I want to tell you. This is it. Okay, so this is the perpendicular over here, point of coincidence. Now suppose I drop a line over here, okay, on either side. It's going to cut the perpendicular at a distance of 1 SD, 1 standard deviation on either side. Okay, now if I have a pink line, okay, here, so this is going to cut the base at a distance of 2 standard deviation on either side. And if I draw a third line, this is going to cut the perpendicular at a distance of 3 standard deviation on either side. Okay, so you have 3 colors. Now over here they look very far spread, but actually they are very close to each other. What you need to remember, mean plus minus 1 SD always covers 68% of observations, for you to remember. Okay, mean plus minus 2 SD, guys, always covers 95% of observations. Okay, and mean plus minus 3 SD always covers 99%. But if somebody asks you, mean plus minus dash SD covers 100%, it is infinite. We don't have any number over here. Okay, that is why you can see that the tails of the curve, okay, tails of the curve are never touching the baseline. Okay, they are never touching the baseline. Are they touching the baseline, tails of the curve? No. But these 3 formula are very important. Once in an AIMS paper, they asked mean plus minus 1.64 SD covers 90% observation. But at least remember, 1 SD covers 68, 2 SD covers 95, 3 SD covers 99% standard deviation. Got it, everybody? Okay, so see, not true about standard normal curve. Equal distribution, yes. Total area under the curve is 2. Again, this is wrong. It is 0.5 plus 0.5, which is equal to 1. Mean is 0, standard deviation is 1. A study had a normal distribution where median was 200 and standard deviation 20. So 68% observation will fall between. Now you know, for a normal distribution, mean is equal to median is equal to mode, right? So even if it's written over here, median is 200, mean is also 200, and 68% observation के लिए कौन सा formula, which one we have to use? Mean plus minus 1 SD covers 68% observation. Yes, we have already done it. So over here it is 200 plus minus 20. This covers 68% observation. So this becomes how much? 180 to 220. Right? If I asked you 95%, you will just do it 200 plus minus 2SD. 2SD covers 95%. So that is 200 plus minus 2 into 20 covers 95. So that is 200 plus minus 40. So your answer would have been 162, 240. Okay, this is the application. Next is skewed distribution. Skewed distribution hota hai whenever outliers are present in a data set. Okay, so when outliers are present in a data set, they are going to tilt your data. So it's going to become skewed. Now, either it could be a right-sided skewness or guys, it could be a left-sided skewness. Look at the direction of the tail. To decide skewness, look at direction of tail. Okay, here it is pointing towards the right side. So this is what right-sided skewness, or you could also say what is it? Positive skewed. Okay, right means positive skewed. Now look at the direction of the tail over here. What is it? Which side is it pointing? It's pointing towards the left side. So this is what? Left-sided skewness. Okay, left-sided skewness, or you could also say what? This is what? Negative skewed, everybody. Now statistically, what have we derived? For right-sided skewness or positive skewed, always remember this equation: mean is more than median is more than mode. But for left-sided skewness, statistically, what have we derived? Mean is less than median is less than mode. Okay? And suppose I draw 3 lines over here. Okay. Now, if I ask you, which is the median over here? Always remember, median is the middle line. So, this middle line on both the sides is the median. Now, you know, for a skewed data set, what do you think is the most affected? Obviously, mean, right? Mean is the most affected in the skewed data set. Okay, mean is the most affected. Mean is the most affected in skewed observation. So, wo niche, this is below, mean. Okay. And mode is not bothered. It's kind of the least affected. So, it is at the topmost. But which is the best measure of central tendency for skewed data set? Median. Okay. So, depending if there are outliers present, my data set will be tilted towards the right or left. Look at the direction of the tail. If it's pointing towards the right, right-sided skewness, left-sided skewness. And statistically, you need to know these values. Okay. So the question comes for any data set, they've given you mean is 200, mode, median is let's say 100, okay, mode is 50. They ask you which type of distribution, normal, right-sided, left-sided skewness. So here you can see that mean is more than median, which is more than mode, right? So this automatically becomes positive skewed. Okay? Hello dear students, so welcome back to this rapid revision video on biostats part 2. Okay, so in this we're going to look at again some conceptual topics like revised types of errors, revised parametric, non-parametric tests, look at the various graphs and all of those things. Okay, so now I'm going to make this topic a little easier for all of you by giving you out the golden points on this topic of types of errors. Now as you've seen in the main lectures also, whenever we are doing any whenever we are doing a study design or whenever we are doing applying biostats, some errors can emerge. Okay, and what were the two broader classification of errors that you have to remember? Type 1 error versus type 2 error. So since this is a rapid revision video, I'm going to sum up this topic in a few golden points for you. Okay, so let's do the difference between straight away the difference between type 1 error and what is type 2 error. Now, how had we learned it? If you remember, suppose I make a new drug, alright, suppose I make a new drug, okay, so I obviously would want my new drug for any disease to be better than the already existing disease in the market, okay, so we always, without doing any research, I cannot say without comparing with an existing drug that my drug is better, okay, so in order to do that, always a H0 is set. H0 means, if you remember, null hypothesis. What is the meaning of null hypothesis? Null hypothesis simply means that there is no difference, okay, there is no difference in the treatment of a disease, okay, in the treatment of a disease between the two drugs, okay, there is no difference in the treatment of a disease, between the two drugs. There is no difference at all. So that is the null hypothesis. And what is the alternate hypothesis? Obviously, alternate hypothesis would be that there is a difference. Okay. And mostly the new drug is better. Okay. New drug is better. Okay, new drug is better. But always the errors when we encounter in establishing that this fact will be dealt in terms of null hypothesis. We will either be accepting a null hypothesis or rejecting a null hypothesis. So in doing that, two types of error arise, type 1 and type 2. How will you remember it? You'll remember type 1 error from the word true and type 2 error from the word false. Now you remember, whenever you're given a question, we always write mark true or false. Okay, so the first thing is true and the next one is false. Now what is this type 1 error? So look over here, very easy. Remember the word true. So that means H0 is T for true but rejected. Okay, and what is this type 2 error? H0 is false, F for false, but A for accepted. Okay, so what is type 1 error? Null hypothesis is true, okay, T for true, but rejected. And what is type 2 error? The word associated with it is false. False means H0 is false, F for false, but accepted. So now what does this mean in type 1 error? That null hypothesis is true. That means in reality, I'm just going to quickly revise it, okay. In reality, H0 true means there is no difference, okay, in the treatment of a disease, okay, in the treatment of a disease, alright, between what? Between two drugs, okay. But this reality has been rejected. But based on clinical trial, what has been done? But based on clinical trial, we have done what? Rejected a true H0 and what did we do? Launched drug in the market. Okay, launched drug in market. Are you understanding? H0 is true but rejected. That means in reality, H0 is true. There is no difference in the treatment of a disease between the two drugs. But rejected. Based on the result of a clinical trial, I have shown a difference and launched my drug in the market. Okay, so H0 T for true but rejected is type 1 error. Okay, and H0 false but accepted. What does this mean? It simply means that in reality, H0 is false, meaning new drug is better. Okay, but based on a clinical trial, we could not show, alright, and did not launch the drug in the market. Okay, did not launch drug in market. Okay, so H0 is false, but we have accepted a false null hypothesis and we didn't go ahead to launch a drug in the market. So this is the first difference. What is the second point that you have to remember over here? Type 1 and type 2. Okay, so type 1 error is an indicator of a false positive trial. Type 2, a false negative trial. Okay, here what we have done, we've shown a false positive trial. The drug is not good, okay, implies drug not good, but shown to be good, okay, shown to be good. The drug is not good, but we showed it to be good. And in false negative trial, what is there? The drug is good, but could not show, okay, but we could not show. Okay, so which type of error do you think is more serious, type 1 or type 2? It's a false positive. The drug is not good, but you have shown it to be good, putting people's lives at risk. So type 1 error is always more serious than type 2 error. The drug was good in type 2 error, okay, but I could not show it. It's okay. There is already an existing drug in the market. Okay, so what are the golden points you will remember? For type 1 error, remember the word true. T and R, null hypothesis true but rejected. So the drug was not good, but I showed it to be good and launched my drug in the market, which is actually not good than the better drug, than the existing drug. Type 2, remember the word false. F say H0 false but accepted. Okay, the drug is actually good, but we couldn't launch it. So false positive trial is type 1, false negative is type 2. Type 1 error is more serious than type 2 error. So this is the first part. Okay. All right. Now type 1 is a very serious error. The question arises, how much of a type 1 error will you allow in a study? So that thing is given by what is known as p-value. Okay. What is p-value? P-value, everybody, is the probability. Okay. Probability of committing what? Probability of committing a type 1 error. We know type 1 error is more serious. Okay. So what are the chances of committing a type 1 error? Should I allow it to be committed 10 times out of 100? 5 times, 1 times, what? Okay. So remember, the maximum threshold of committing a type 1 error. Okay. The maximum threshold of doing what? The maximum threshold of committing a type 1 error, okay, has been set at 5%. And this, everybody, is known as alpha level of significance, okay, alpha level of significance. These are other golden points, okay. P-value is what? The probability of committing a type 1 error, and the maximum threshold of committing a type 1 error is set at 5%, which is alpha level of significance. But in any study, for the result to be statistically significant, p-value should be less than alpha, which implies p-value should be less than 0.05. If p-value, everybody, is less than 0.05, it means what? It means that the results are statistically significant. Okay. See, p-value is the probability of committing a type 1 error, and the maximum chance of committing a type 1 error, the maximum threshold, the cutoff of committing a type 1 error is set at 5%, which is known as what? Alpha level of significance. And for my results to be statistically significant, my p-value should be less than alpha, meaning should be less than 0.05 only. Then only I'll say my results are statistically significant. So p-value less than 0.05 means results are statistically significant. In simple words, what it means? Results are statistically significant. So this means, in simple words, it favors what? In simple words, it favors alternate hypothesis. Okay, p-value less than 0.05 means results are statistically significant. So in simple words, it means that it favors alternate hypothesis. That means new drug is better. So whenever you will get p-value less than 0.05, it means the new drug is better. In other words, see, suppose for a researcher got P1 as p-value as 0.02. Another researcher got, this is researcher 1, p-value is this. For researcher 2, p-value is 0.05, and for researcher 3, it is 0.08. Whose results are statistically significant? Remember, only this one. Okay, this is statistically significant. Simply for exam purpose, remember, when I say statistically significant, it means that a new drug is better. It's favoring alternate hypothesis. Even when it is equal to 0.05, it is not statistically significant. Okay, even if it is equal, it means it is not statistically significant. Even it comes out to be equal to 0.0, it has to be less, and this is not significant. Now, in other words, if somebody asks you, iska actual kya matlab hai? See, when I say that p is equal to 0.02, it simply means that if a study is conducted 100 times, okay, if a study is conducted 100 times, okay, then only 2 times, okay, what was P? Probability of committing a type 1 error. So only 2 times we reject a true H0. 2 times is even less than 5, okay. So it's only 2 times we reject a true null hypothesis, which could happen by chance, okay, which could happen by chance. By chance this is happening, that 2 times I am rejecting a true null hypothesis. Rest 98 times, okay, it favors what? It favors alternate hypothesis. Okay, it favors alternate hypothesis, which means what? new drug, better. Okay? So just remember this. See, for type 1 error, remember the word true. H not true but rejected. Type 2 error, H not false but accepted. Type 1 simply means new drug was not good but I showed it to be good. So false positive. Type 2 means new drug is good but unfortunately I couldn't show it in my clinical trial. So false negative. Which is more serious? Type 1 is more serious than type 2. Since it's an error, how much of it will you allow? That is given by p-value. So p-value is the probability of committing a type 1 error. Now what is the maximum chance up to which or maximum threshold up to which you can commit a type 1 error? That is given by alpha level of significance, okay, which is set at 5%. So for your results to be significant, that means when will I call the result significant? When the new drug is good, okay, it's favoring alternate hypothesis that jo tumne drug banaya, the drug that we've made is good. So that should be less than 5%, meaning less than 0.05. Okay, so like over here, it is 0.0 times, so it's only 2 times I'm rejecting a true null hypothesis. Now, if it's only 2 times, it could happen by chance. Rest 98 times my results are significant, and that's what I'm showing it. Okay, so that's the first part. See, type 1 statistical error, just remember the word true. Null hypothesis true, but rejected. Which one is type 2? For type 2, remember null hypothesis. For type 2, remember the word false. So, null hypothesis false, but accepted. This one over here is type 2. Another way how it is asked, see, a randomized trial comparing the efficacy of 2 drugs showed a difference between the two. So, a clinical trial, randomized trial means over here, clinical trial. It has shown a difference. Okay, p-value has come less than 0.05. But in reality, the 2 drugs do not differ. So, in reality, 2 drugs do not differ. That means, in reality, H naught is true. But trial has shown. Okay? But based on clinical trial, what has happened? Based on clinical trial, difference is shown. So, what is this? Of course, this becomes a type 1 error. Okay, in reality, H naught is true, but based on clinical trial, okay, a difference is shown, putting people's life at risk. False positive. Okay? Okay. Next, so this we have already done. P-value is probability of committing a type 1 error. And what is alpha level of significance? This is nothing but maximum threshold, which is set at 5%. And your p-value has to be less than 0.05 for the results to be what? For the results to be statistically significant, everybody. Okay? Alright, moving to the next thing now, let us quickly see what is power of a test. Okay, now remember, power of a test is given by the equation 1 minus beta. Now, what is this? What was type 2 error? Okay, type 2 error, beta. Okay, alright, remember, alpha is type 1 error. It's denoted by alpha, and beta is type 2 error. Okay, type 2 error. Now, what is beta, guys? Type 2 error kya tha? If anybody asks you what is type 2 error, just remember this. Type 2 error is equal to the word false, right? So, it was that H naught is false but accepted. Okay, this simply means that H naught false tha, your drug is good but we could not show it. Okay. Now, what do you mean by power? Power means that if a statistically significant difference exists, okay, if a statistically significant difference exists, okay, then the test should be able to show it. In simple words, able to show it. Okay, if a statistically significant difference exists, that means if the new drug is good, then the test should be able to show it. And what was type 2 error, everybody? The new drug is good, but unfortunately we could not show it. Therefore, power ka formula ho gaya 1 minus beta. Okay, always remember, power of a test, okay, can be increased by, how? Power of a test can be increased by reducing which error? Reduce beta error, obviously. And how will you reduce beta error? If you increase the sample size. Okay? This is very important. And what is the minimum power that a test should have? Okay, minimum power. Okay, remember, minimum power for any test, minimum power of any test should be how much? At least 80%. Okay? Alright. So beta error was that the new drug is good, I couldn't show. And power is, if the new drug is good, show it. Therefore, power becomes 1 minus beta. Okay, increase the sample size is decreases type 2 error and power increases. Okay, so that was very, very important first part. Now, what are these two terms? Always remember these two terms, confidence interval, confidence level, they are used when we are considering samples. And you remember when we consider a sample, what is the measure of dispersion used? The measure of dispersion used is standard error. Now, the maximum threshold, okay, of committing a type 1 error was set at 5%. Now, what is 100 minus 5? 100 minus 5 is 95%. So, what is this 95%? This is the confidence level. Okay, whenever I do a study, I have to be 95% confident that whatever I am calculating, okay, is going to, whatever I calculate, okay, is going to lie within a defined range, okay. So, here whenever you see this confidence interval and confidence level, here we have to take standard error into consideration. For any test to be good, at least we have to be 95% confident. Now, I'll tell you, suppose this is a population of 10,000 people, okay. We have to estimate hemoglobin. Can I do it for all the 10,000? No. So, I take out a sample of 500 people. Okay, and I estimate the hemoglobin. So, sample hemoglobin comes out to be, let's say, 10 gram per dl. Okay, now using this sample hemoglobin, okay, using this sample hemoglobin, alright, we calculate hemoglobin, alright, hemoglobin of this population. Okay, now since we use a certain value to calculate the hemoglobin of this entire population, I can't give an exact value. So we calculate a range of values. And how confident I am that the population value is going to come within that range. Like suppose we use this 10 gram and I got the hemoglobin of the population between, using this, okay, between let's say 8 and 12. Now, how confident I am that yes, the hemoglobin of this population lies between 8 to 12. I have to be at least 95% confident. So, I'm using a sample mean to estimate the mean hemoglobin of the population. And when I use this process of estimation, guys, we need to be at least 95% confident. If I'm 99% confident, even better. So how do we do this? And this comes, since we're talking about samples, we'll use standard error. So over here comes two things where you have to calculate confidence interval of mean. Okay. Confidence interval is the range of value. Okay? Confidence interval of mean, and there is a confidence interval of proportion. So always we have to at least be 95% confident. So 95% confidence interval of mean ka formula kya hai? What is it? Mean, whatever will be given, plus minus, since it is 95%, here it is 2, and since we are talking about confidence interval, I always told you, you will take the word standard error. Okay, whenever you're talking about confidence interval, it means you're referring to samples. So, standard error. And what will be confidence interval of proportion? Instead of mean, it will be proportion or whatever prevalence has been given, plus minus 2, standard error of proportion. Okay, so remember just one thing, whenever you get to calculate confidence intervals, okay, you will use standard errors. So I'll show you a calculation which will make it more easy. See, intraocular pressure was measured in 400 people, N is 400, mean was found to be 25, and standard deviation was recorded as 10. 95% confidence interval. They are not going to ask you to explain. They'll ask you this formula. So 95% confidence interval, that means I have to use for 95%. So this is mean plus minus. Now 95 है, so this यहाँ पे 2 आ जाएगा. And since it is mean is given, we will use standard error of mean. So what is mean given to us? 25. What is standard error of mean? That means 2 into standard error of mean used to be standard deviation upon square root of n. So this is 2 into standard deviation upon square root of n. So this is 25 plus minus 2 into, what is the standard deviation? 10 upon square root of n, 400. Okay. So this will come out to be 25 plus minus 2 into 10 divided by 20. So 25 plus minus 1. So that is how much? 24 to 26. Yes. So I am 95% confident, okay, 95% confident that mean intraocular pressure, okay, of the population which we have calculated using this sample mean is going to lie between 24 to 26 mmHg. Got it, everybody? Okay. But in case the question comes, what is 95% confidence interval in a study? Estimated prevalence is 10 and 100 is the sample size. Okay. Now here I have not been given the mean value. I have been given prevalence of 10%. But I have been asked to use confidence interval. So I'll use what? Confidence interval of proportion. So for that, what is the formula? P plus minus, since it is 95% 2, but instead of taking standard error of mean, we will take standard error of proportion. So P has been given to you as 10 plus minus 2 into square root of PQ by N. Okay, so 10 plus minus 2 into P is 10. What is your Q? Q automatically will be 100 minus 10, 90%, right? Divided by 100. So this will come out to be 10 plus minus 2 into square root of 900 by 100. So square root of 3. So 10 plus minus 6. Okay. So 10 plus minus 6 means 4 to 16. So I'm 95% confidence that the prevalence of the population will lie between 4 to 16%. Just remember one thing, guys. Whenever you get to calculate confidence interval, you'll get either mean or proportion. So we have to consider standard error of mean or standard error of proportion. You cannot forget that. Okay? So that was the first part. How you'll remember the types of errors, what is power and confidence interval and confidence level. Okay. Now next is test of statistical significance. See, what was test of statistical significance? Now obviously when you are doing this entire process of accepting, rejecting, null hypothesis, when that has been done, we need to show if the result is statistically significant, we need to apply certain tests also. Okay. So it is further divided into two types. Okay. Parametric test and non-parametric. Now here mostly they ask you the interpretation of a few tests, which we will do it. Okay. So when you talk about parametric test, non-parametric, parametric test, everybody, is used when we are taking into consideration quantitative variables. Okay. Non-parametric is used when we are taking into consideration what? Qualitative variables. Parametric means, what do we mean? What are we comparing? We compare means and SDs, okay, since standard deviations. But in qualitative, can we express in means and SDs? No. So we can express in percentage and proportions. First, let me write the difference. We are comparing what? Percentage and proportions. Now, parametric test, remember, is always used, okay, for what? Normal distribution. And non-parametric is always used in case of skewed distribution. You already know what is normal and skewed. And parametric test, everyone, is more powerful. Okay. Non-parametric, guys, is less powerful. ठीक है. So the important thing is when we are comparing quantitative variables, like if I have to compare height, if I have to compare weight, when I can express anything in means and SDs, I'll use parametric. Non-parametric, when I can express the dependent variable only in terms of percentage and proportions, like breast cancer or something like that, okay? Obesity, something like that. So over here, you have to remember the examples of the test, okay? So how have we learned it? Parametric and non-parametric. Remember, for parametric, you will always remember that we are referring to mostly alphabets, meaning what? T-test, Z-test, ANOVA. Non-parametric test may we have very, very fancy names. Okay. So in parametric, there was a person known as student. He gave student T-test. Now student T-test, so T is an alphabet, so student T-test. This could be of two types, okay, paired and unpaired. Alright, unpaired is also called as independent, guys. But student gave both, paired and unpaired, it can be both. Paired means whenever you have to compare mean in one group, okay, before and after an intervention, before and after an intervention. Like compare mean hemoglobin in a group of dengue patients before treatment and after. So you are comparing mean hemoglobin, it's quantitative and in one group, so paired. What is unpaired? We have to compare mean in two groups. Okay, like mean hemoglobin in a group of dengue patients versus malaria patients. And what is the next one? Alphabet A, ANOVA. ANOVA stands for analysis of variance. Okay, it stands for analysis of variance. Here we are comparing what? We compare mean in more than two groups. Whenever you have to do that. Mean hemoglobin in a group of dengue, malaria, chikungunya patients, okay? And there is one more, Pearson's correlation coefficient, which you will just see in graphs, okay? Pearson's correlation coefficient. So these are the types of parametric test. Usually you will be asked about t-test interpretation or ANOVA interpretation. On the other side over here for non-parametric, okay, everybody has a counterpart. Like for paired t-test, we have another test which was discovered by Wilcoxon, which is known as Wilcoxon sign rank test. Also, there was one more, McNemar test. At least the names you need to know in the revision videos. Unpaired may, what is it? Discovered by Wilcoxon only. Wilcoxon rank sum test. Okay. And there is one more, Mann-Whitney U-test. See, all fancy names. For and are very common. Two groups ke saath you can start using chi-square test. Three groups you have to compare. Please use chi-square test. And there are two more names, fancy names which you must know. Kruskal-Wallis and Friedman test. Okay, Kruskal-Wallis and Friedman test. And Pearson's correlation ke yahan pe kya ho gaya? What is it? Spearman's correlation coefficient. Spearman's correlation coefficient. Okay, so remember one thing, parametric is all alphabets, non-parametric is all fancy names. Here you will get the interpretation of paired, unpaired and ANOVA test in, but mostly on the non-parametric side we'll be asked about chi-square test. Two more tests, remember again Z-test. Z-test again is an alphabet. So what is it? Since it's an alphabet, I told you all alphabets are going to be parametric. So this is what? This is a type of parametric test, okay, which is used when? Which is used, everybody, okay, which is used in place of t-test, alright, when the sample size, everybody, in place of t-test, when the sample size is more than 30. And again another test with a fancy name, see, Fisher's test. At least you have to know the test. Fisher's, okay, so this is what? This is a non-parametric test, okay, this is a non-parametric test which is used in place of what? In place of chi-square test, everybody, okay, when sample size is less than 30. Okay, so that is important for Fisher's test. Okay, now see, suppose you have to compare mean hemoglobin in a group of malaria patients before and after treatment. So mean hemoglobin, mean mein you will use parametric, and in a group, so this is a single group before and after. So what will you use? Paired t-test. But if you have to compare mean hemoglobin in a group of malaria, dengue, so mean hemoglobin obviously quantitative, but two groups, so independent or unpaired t-test. So student can be paired also, unpaired also. And in a group of malaria, dengue versus yellow fever, so it is three groups, so ANOVA. Now just have a look at some of the examples. See, all are non-parametric tests except. So I told you for non-parametric test, remember you have fancy names. Okay, and there is only one alphabet over here, so Z test. Z test is parametric. Okay, alright. Next, a study to compare hemoglobin level was conducted on alcoholics before and after consumption. What are you using? First, look at your outcome variable, hemoglobin. So, hemoglobin is quantitative or qualitative? Of course, hemoglobin is quantitative. Yes, you can measure it in a unit, gram per DL, you can compare it. So, it's quantitative, right? So, and before and after consumption, so you're doing it in a single group. So, obviously, you'll use a parametric test in a single group, paired t-test, okay? Test used to compare to qualitative data. Qualitative means we have to use a non-parametric test. So, which is the non-parametric test over here? Chi-square test, okay? The appropriate statistical test to find out obesity as a significant risk factor for breast cancer. Now, over here, what are you comparing? So, look at the outcome variable, breast cancer, right? Breast cancer, can you calculate mean of breast cancer? No. You can definitely express percentage of breast cancer, that 50% women are have suffering from breast cancer. So, I know that my outcome variable can be expressed in percentages. So, I need to use a non-parametric test. So, this is out, this is out. Now, most commonly used non-parametric test is chi-square. Okay. Now, over here, signed rank test is used only for one group. Okay, now here we have a 2x2 group. How? See, breast cancer, yes, no, and over here basically obesity. Obesity also yes, no. So, you can see this makes it a 2x2 table. Okay, so most commonly here we will use a chi-square test. Got it? Everybody? So, that was test of statistical significance. Whenever you get a question, look at your outcome variable. Are you comparing quantitative or qualitative? If quantitative, parametric. Okay, parametric, remember, you have all alphabets. T-test, Z-test, ANOVA. ANOVA is more than two groups. Unpaired T-test is two groups. Paired T-test is one group. Z-test is used instead of T-test when sample size is more than 30. Rest all fancy names is on the non-parametric side. Mostly you will be getting the interpretation of chi-square. Alright, now next quickly let's have a look at graphical representation of data. So for quantitative data, which graphs can we create, and for qualitative data, which graphs can we create? Okay. So, for quantitative data, everybody know the names. Histogram. We can create what is known as frequency polygon, line chart or line graph. Okay, we can create a cumulative frequency curve, or you could also say ogive, and we can create scatter plots. These are the most important ones. Okay. On the qualitative side, when you have to represent by graphs, you have a bar chart, which is simple multiple component, which you will see in just a while. We also have pie chart, pictogram, spot maps, and also Venn diagram. Okay, so you could be asked, all are quantitative, all are graphs to represent quantitative data except, or which one of the following is used to represent qualitative data? Okay, so that was the graphical representation. Now look at this. Now let us start. Okay, let's look at some images. What is this? Now here you can see profit is in percentage. So percentage means we are talking about qualitative variables, right? And here you can see a gap. Okay, so here we are drawing what? A bar graph. Okay, bar graph is used to represent the frequency of discrete variables. Okay, discrete variables. Here you can see also it's expressed in percentages, guys. Okay, right? So we're not expressing in means on SDs. We are talking about qualitative data. So discrete. So this is a simple bar. Bar ko you can just 3-letter gap. Gap is also 3 letter. Okay, this is simple bar. So here this is simple bar. Here this is a multiple bar diagram. Okay, like in the first quarter, how much revenue was generated in Kent, Lincoln, Mersey, York? So again, frequency of discrete variables, bar diagram. In a simple bar, I've divided it into 4-5 parts. So this is what? Component bar. Remember, bar diagram is used to represent frequency of discrete variables. So which one is there? See, city X, blood group, we have divided that into O, A, B, B, A. Similarly, Y and Z. So again, over here, we are expressing blood group. Blood group is continuous or discrete? Of course, it is discrete. Either your blood group A, B, or O, you can't lie in between, right? So this, but in a simple bar, in one bar, we have divided it into components. So this is a component bar diagram. Okay, what is this? We all know pie chart. When simple, we have to talk about percentage and proportions. We use a pie chart. Like example, explain to a community the importance of recommended dietary allowance. Like in your diet, you should have 10 to 15% of proteins. Okay, then 15 to 30% fats, 50 to 70% carbohydrates. So you can use a pie chart. This is a pictogram. Okay, pictogram is used for a layman who cannot understand all these percentages and proportions. Now see, a popular method of presenting data to the man in the street who cannot understand orthodox chart. Can you use all these line diagram, frequency polygon, histogram? No, we'll use a pictogram. Now what is this? Now here you can see we are using height. So when I'm using height, this is a continuous or discrete variable. Of course, it's a continuous variable. It's a quantitative data. So when we have to represent, guys, frequency of continuous variables, okay, frequency of what? Continuous variables. So when we have to use frequency of continuous variables, we will make what? A histogram. See, there is no gap because it's a continuous variable. It can take up many possible values and also it can take up in between values. So here, no gap. Okay? So frequency of continuous variables, histogram. Frequency of quantitative data, histogram. Right now you will see scatter. Scatter mein the word is used as correlation. Line mein the word is used like trends. Abhi we are going to see. Now if I join the midpoints of this histogram by straight lines. Okay, so what have we done? We have joined midpoints by straight lines. So this makes it what? This is what? This is nothing but frequency polygon, everybody. Okay, we have joined the midpoints by what? We have joined the midpoints, everybody, by straight lines. So when we join the midpoints by straight lines, it is called as a frequency polygon. Okay, and when we have wide class intervals, the frequency polygon loses its angulature and becomes a curve. Okay, this is nothing but a line diagram. What does this do? This is used to represent the trends of an event with time, okay, or incidence of cases with time. What is it representing? Incidence of cases with time. Like for a disease, the cases are increasing, decreasing. So whenever you see the word trend of an event or incidence of cases, you'll use a line diagram. See, change of incidence of disease, line diagram. Okay, best chart to represent incidence of disease, line diagram. Histogram mein hoga frequency. Okay, don't get confused. This is frequency of continuous variable. Bar chart is nothing but frequency of discrete variable. And what is scatter diagram? This represents the correlation between continuous variables. Okay, what is this? Now here you see that there is no dip. Okay, there is no dip. So this one over here is nothing but cumulative frequency curve. Okay, what is it? Cumulative frequency curve. Or this is known as ogive. Here we are seeing a constant increase in cases. Okay, like it happened in the case of COVID. Okay, in 2021 from January to May. There is no dip. Even if they ask you, recurrent cases can be represented by cumulative frequency curve. Okay. What is scatter diagram? Scatter diagram, remember, is used to represent correlation between two continuous variables. Okay, and this is represented by a correlation coefficient. Okay, by a correlation coefficient. The value of correlation coefficient lies between -1 to 0 to +1. Meaning, this can take up 3 graphs. Can you see this? All the dots are over here. Or it could be second one like this and dots are like this. Or it could be like this and the dots are all over here. Now here, if the x-axis rises, the y-axis also rises. This one is, and all the dots are on the line. So this is perfectly positive, where r will be equal to +1. Here, there is no association between x and y-axis. So here, r is equal to 0. And look at this, if x-axis rises, the y-axis decreasing. This is what? Perfectly negative, everybody. R is equal to -1. So you can never have correlation coefficient value more than +1 or less than -1. Like if suppose you get a question where somebody calculated correlation coefficient as R is equal to +1.64. Is this possible? No. This is not possible. Okay. So the researcher calculated it wrong. So you must know perfectly positive, perfectly negative and this one. Okay. Alright. So that is very, very important. So graph to correlate to quantitative data, we have scatter diagram. Whenever you see the word correlation, it is scatter diagram. Now, box and whisker plot we have read before. Box and whisker plot are used to represent, guys, actually quartiles. Quartiles divide my data set into 4 equal parts. You can refer in the main lecture also. Now, I just wanted you to know revise the image of the box and whisker plot because it is very in these days. Okay, now can you see this? This middle one is the box and these are the whiskers. This is Q1, Q2, Q3. Now, first quartile, second quartile, the second quartile is dividing it exactly into 2 halves. Can you see? So, there are no outliers over here. Can you see? No outliers because the gap is exactly equal on both the sides. So, this is which distribution? Normal distribution. Okay, this is representing normal distribution. But in case you get a graph like this in your exam, okay, this is what? Q1, Q2, Q3. Now, where is the gap more? The gap is more on, this gap is more on which side? On the right side. So, here we have more outliers on the right side. So, on the right side, if I draw now, this will be the tail. So, this becomes right-sided skewness. Wherever you see the gap more, that is the skewness. That's the side. Look at this. Now look at the middle one. Over here, the whiskers are also equal. The box is also equal. So this is normal. But look at A. Look at the first one. The gap is more on the right side. So now if I have to draw, it will come like this. This one is right-sided skewness. And we know for right-sided skewness, mean is more than median is more than mode. Here, where is the gap more, everybody? It's more on the gap, more on the left side. You can also make it out by the whisker. Whisker is also longer on the left side. So here, what does it become? Like this. So this is what? Left-sided skewness. For left-sided skewness, mean is less than median is less than mode. Okay? So you can see. Now suppose you get this where you've not got a horizontal vertical one. So what have I taught you in the main videos also? Rotate it clockwise. Rotate the first image clockwise, everybody. So even if you rotate this first image clockwise, guys, you can see over here that it is normally distributed. The gaps are equal on both the sides. So one is normal. But if you look at graph number 2, let's rotate it, everybody. So if you rotate it also, where is the gap more? On the, here the gap is more on the left side. So left-sided skewness, negative skewed. And look at the third one now. Try to rotate the third one, everybody. So agar aap third one rotate karoge, where is the gap more? The gap is more on the right side. So positive skewed. So this is your answer. Okay? If you get horizontal, no problem. If you get vertical, don't forget to rotate it clockwise and look where is the gap more. Okay? Alright, what is the name of this diagram? This is nothing but Venn diagram. Maybe it can come in your exam. Okay? Alright. What is this? Very, very important. Spot maps. This is used to represent what? local distribution of cases. Okay, and who had drawn this, guys? This was drawn by John Snow, right? Father of epidemiology during the cholera epidemic in London. Okay, so the question comes, does spot map show local distribution or national or regional distribution? So remember, spot map shows us local distribution of cases. Okay, what is this? This everyone knows. This is a stem and leaf plot. You've done box and whisker, forest and funnel in epidemiology. Okay, so that was graphical representation. Now see, when you talked about correlation was simply the association between two variables. And if suppose one variable increases, what happens to the other? Is it increasing or is it decreasing? But regression is used when you want to predict the unitary change. Means if one variable increases or let's say decreases by 1 unit, okay, what happens to the other variable? Okay, what happens? Increasing or decreasing was given by correlation. But by how much unit? Okay, what happens to other variable? Or unitary change in the other variable. Okay, unitary change in other variable is given by regression. So there's a regression equation which would come in your exams. Y is equal to a plus bx. Y is always the dependent variable. Okay, like suppose you are studying the effect of age, religion, like all these things on hypertension. So hypertension is the dependent variable. X are the number of independent variables that you have. B is the regression coefficient. A is the constant. So Y is equal to A plus BX. Okay. This thing is the regression equation which can come in your exam. Okay. So this is the equation. Now, very important thing is that what are the different types of regression that you have. So remember, if you see the word unitary change of one variable from the other variable, that is predicted by coefficient of regression, everybody. Okay. Now look over here. Y is equal to A plus BX. Can you see this? Y is equal to A plus BX. Now here, you have this Y is the dependent variable and here you have only one independent variable. So this is a simple linear regression. Okay, but here you have one independent variable which is raised to a power. This independent variable, everybody, is raised to a power. Okay, so this will, whenever it is raised to a power, it becomes what? Curvy linear regression. Now look at the third one. You have three independent variables and none of them are raised to a power. So this is what? Simple ki jagah multiple linear. But if you look at the fourth one, first independent variable and the third independent variable, all of them are raised to a power. So even if one independent variable is raised to a power, we will use the word curvy linear. And here we have more than one independent variable. So this becomes multiple curvy linear regression. You could be asked to identify. They can give you, suppose, the second equation and they can ask you what it is. Okay. Also remember one more thing, guys. Where do you use logistic word? Okay. Logistic regression is used whenever my dependent variable, alright, can take up only two values. Like yes or no. Okay, so I've just summed it up for you. See, linear regression describes effect of one independent variable on a dependent variable. Multiple means more than one independent variable. Non-linear is more complex. Logistic regression describes effect of multiple independent variable. It could be quantitative, qualitative or mixed on dichotomous qualitative. Like presence or absence of disease. Okay, let's say hypertension. This is the dependent variable. Effect of age, effect of religion, effect of gender, anything. These could be anything qualitative, quantitative. But dependent variable has to be a dichotomous. Then only you can use logistic. Okay? Alright. So that was about regression. Always remember we talk about unitary change. Then only we use regression. There's a concept of probability, guys. Probability means what are the chances? What are the chances if I skip a coin? What are the chances of me getting heads and tails? So in the main videos also you've seen you'll use a rule of addition or multiplication if they are mutually exclusive events. Meaning either them occurs. Like either a male or a female. Either head or tail will come. So we use the rule of addition. But when is rule of multiplication used when we have joint probability of independent events. Okay, so here what are the words that are used? Like two independent events and one does not affect the other. Then we use a rule of multiplication. Lastly, what are the different types of sampling we have studied? So sampling mein you have random sampling methods and you have non-random sampling, right? So random sampling methods mein what were the names that you have to remember? Simple random sampling, okay, stratified random sampling, systematic random sampling, cluster random sampling, important, multi-stage and multi-phase sampling. ठीक है? And when you talk about non-random sampling, so random sampling is very, very important. It is probability sampling. Non-random is non-probability. Non-probability of what? Or probability of what? Probability, like you had studied, random means equal and known chance, right? Probability. That means everybody has an equal and known chance of going into the groups, okay? Non-random sampling or non-probability sampling may everybody, what we have to say, we have to use the names, okay? So here it is convenient sampling. Okay, what are the other things that could be used over here? Very, very important. There's a term known as snowball sampling, quota sampling. Okay, these are certain non-random sampling method. Remember, convenient is like I can select my sample based on my wish. I want to do a study on adolescents. I go and stand outside the mall and any adolescent that I see, I select him for my study. Okay, snowball sampling is used for hidden populations. Okay, like suppose I want to do a study on commercial sex workers. They are not easy to get, or homeless people, or migrant. Okay, so if I happen to find out one, I can give them my questionnaire and then they pass on to the others. Quota sampling is again we divide it into different quotas, and from that quotas, like male group separate, female group separate, from them non-randomly select anyone I want. We'll not use any random procedure over here, but I'll just quickly go to the image. Now look over here, this is simple random sampling. Simple random sampling ke liye what we had studied, we need a sampling frame, guys. I need an entire list, like I can do it in a college where there are 10,000 students, so I need that frame of 10,000 student, okay, and this could be achieved by, and then I can randomly select my participants either by a lottery method or chit method or flip a coin method, okay, flip a coin method. This is what is simple random. I need a sampling this thing. This is systematic. No, first let's see stratified. In stratified random, we convert what? Heterogeneous into homogeneous. Can you see this? So first there was a mix of population, then we've converted into a group of yellow and separately into a group of blue. And then from this group, we can use a random method to take out participants. Like this has 6 people. 9. So in the final sample, the people that I need to include, I can take from here 2 and I can take from here 3. Right? Okay, 2 people from here I can select and 3 from here. That will be a true representative. I've divided them into different stratas and then I'm using probability proportional to sample size to select my final participants. So you'll see an image like this only. Okay, you've had different stratas and within strata, I am using a simple random. Okay, within strata, we can use simple random. Now, what do you do over in systematic? See, in systematic, it is for a heterogeneous population. I don't want to convert it into homogeneous. Can you say it is mixed? But here, what was the buzzword? We take every nth or kth person. Meaning here I am selecting every third participant. Can you see? 1, 2, 3, 1, 2, 3. So whenever you see the word nth or kth participant, we use systematic. And how do you calculate this nth interval? So this is whatever is the total population divided by the sample size. Okay, and last over here you can see cluster. Now you remember cluster sampling mein we had 30 into 7 clusters. Okay, 30 into 7 actually is this thing that we have taken for cluster random sampling when we are doing evaluation of immunization coverage, right? So here we are taking 30 clusters which are naturally selected, guys, naturally selected, and within each cluster we are taking 7 children. These 7 children that we are taking is first come first serve. Okay, and these children target age group is 12 to 23 months that we are taking, not up to 1 year. Okay, in the first cluster, in the first house, I find one child who is 22 months. I take that. Second house I go, I don't find anyone. But in the third house, again, I find one child who is 12 months. I take it. So 30 clusters and 7 children. So total sample size is 210. Now you can see each cluster, everybody has exactly equal numbers. See here there are 5 clusters. Okay, but within each cluster there are 3 participants. Okay, so that is fixed, alright. And when we have to remove the clusters in amongst themselves can vary. So when we have to remove the heterogeneity between clusters, we use what is known as design effect. Okay, which you have studied in the main lecture also. So you just have to remember design effect is used for which sampling? Cluster sampling. Okay. So for simple random sampling, have an entire sampling frame. See, this is an entire sampling frame which is available. Stratified, you can see groups of similar colors and then you're selecting participants from that. Systematic, every third, fourth, fifth, something like that. Clusters, you will see naturally selected groups, but each of them are going to have equal number of participants. All this convenience purposes, snowball and quota. These are methods of non-random sampling. Based on my convenience, I am selecting anybody. Then purposely I am selecting these people. Snowball, see, I gave them, then they passed on to them. Gave the questionnaire to this, passed on to them. Quota, again, like I've divided into similar colors, but now within this I'm not going to use PPS, probability proportionate to sample. I can select anyone I want within a quota. Last thing, how do you calculate sample size? How to calculate sample size? What was the formula? So just remember, to calculate the sample size, everybody, the formula was 4 PQ by D square, right? P is always the prevalence which is given to us. Q is always 100 minus P. D is always absolute error. Okay, so 4 PQ by D square. Yeah, so that's it. Small class, but again, all the things that we have seen right from the first one till sampling are equally important, everybody. Thank you so much.